question 6 on whatever page that was. Page 509. So this is a function as a tangent with tangent to this is 5x plus by is equal to a at the point where x is -3. Okay, find the values of a and b. So Badai, what did you get for this one?
For A, I got 9. For B, I got -16.
Rigel?
The same.
Okay, yeah, so that's correct. If Dustin is watching this later, so you'd have to sub in where x is -3, you get a value for y, and that's your point of contact then, which will help you later on. And then you need to do a derivative, don't you, and use the I suppose you could use the quotient of the product rule. If you make that to the power of a half and bring it up -1/2, you can use the product rule. Okay, it seems that you're okay in that one. The second question 13, was the one where you have to prove that every normal to a circle passes through the origin. So every normal to this circle passes through the origin. All right. Rigel, what'd you do?
Well, I differentiated it, got the tangent, then inversed, got the normal, then used the normal to find the normal equation, and then using that, make a makeshift point on this, like the circle, like say x1, y1, and then assuming that x1, y1 that would also go through the origin, which is 0, 0. You plug in 0, 0, and it works. And then you can say, but that works for everything except when the gradient for the tangent is 0, because then the normal would be an undefined line. But you can just say that is a line that would go along the y-axis, therefore going through the origin.
Okay, yeah, I suppose that makes sense. Badai, did you do the same thing?
I mean, I differentiated it, and I get the dy over dx is equal to -x over y.
Yeah.
And then the normal happens to be y over x. And it turns out that the normal and the tangent both cross the origin. And sorry?
The normal and the tangent both cross the origin. How's that possible?
I know. I mean, I tested 2 different points, and I found that both normals cross the origin, and so I concluded that the normal, every point of this circle will have a normal that will always cross the origin. I didn't.
You can't. Generally, you can't prove something by just putting in numbers, and if it works once or twice, then you can't. It doesn't always follow that. Then you can say that it always works. So you're probably better off doing. So I presume you're both okay at getting the derivative. So you have dy dx is equal to -x over y. I think we did that example before, anyway. For this one, I would do what Rigel did. So let's say pick a point. So when x is, Rigel used x1, I think. I'm just going to call it a. So when x is a, what's the corresponding y point for a? So you would sub it into this equation to find the corresponding y point. So it's going to be, well, a squared. Well, let's do it out. Y squared, I'm not going to find y, but y squared is equal to 1 minus x squared, yeah. And then y is then going to, sorry, I've subbed in a now, because I'm saying x is a. I could use x1, y1, like Rigel did, but I think it's easier to use a different variable. Then I get square root. So the square root of this is going to be plus or minus square root of 1 minus x a equals x. Okay, so that's going to be a point on the circle. That's basically all points on the circle. If it's if it has one, if its x value is this, its y value will be either plus or minus this. Okay, so that's a general point. So as you alluded to, Badai, the gradient of the normal then is going to be the inverse of this, isn't it? And the negative, so it's y over x. All right, and based off the points that we have, the gradient, I can use x and y here, and that would give me a general gradient based in just a. Now, just a. So when I put that in, it's either going to be plus or minus the square root of 1 minus a squared all over a. Okay, so inverted. All right, so that's the general form of any normal slope for this particular circle.
Why is it y squared equals to 1 minus a squared instead of just...
I'm trying to find a corresponding y point for this. So I just rearranged this. So y squared is our original function. So as if you had x was equal to 5, how would you find the y point then? You would bring x squared over, and then so it's just the same thing. So I wanted to form equation in just a. So then, now to have the gradient, I'm going to use y minus y1. I just want to find a general formula for the equation of any normal. And any normal would satisfy, would have a point that would satisfy this, because it would have to be on the circle. That's what I did at the start. So y take away, well, y1 is going to be plus or minus this. So it's going to be minus or plus this. Instead of plus minus, it's minus plus, the opposite of this. 1 minus a squared equals the slope, which is plus or minus 1 minus a squared over a times x minus a. So this is a general equation for the normal. Now, if I multiply this out, what is going to happen is, wow, goodness. You hearing that bike?
Yeah, but it's fine.
I know, yeah, it's just annoying me. So I'm just going to move this over. Plus minus is going to be plus minus as well. So it's going to be, if I multiply this by this, I'm going to get root 1 minus a squared over a times x. That's going to be just this times this. Oh, that's plus or minus. And then it's going to multiply it by a, so the a's are going to cancel. Hopefully we're happy with that. So what we're going to get is plus and minus 1 minus a squared minus plus. Now the plus minus here is a bit weird. So hopefully I've actually swapped this one. This minus a is going to change this to a minus plus. And this one, when it comes over, is going to go to a plus minus. So it's always going to be the opposite. I might have written it the wrong way around. But they're always going to be the opposite signs. Because this one has affected that. Whoever it was, it will change it. Now, whatever it is, these will cancel. So what have I got?
Wait, so every time you move over plus minus to an equal, it'll just cancel each other out?
No. So this moving over, I need to, if it's a minus, I would add it. And if it's a plus, I would subtract it. So in other words, there's there's a subtle difference between plus minus and minus plus. This one originally is plus minus, but now it's multiplied by minus. So if it was a plus, it'll become a minus, and if it was a minus, it'll become a plus. Same thing applies here. You could talk about, changing the sign if you want to talk about it that way. If that comes over, it's minus plus, and then it becomes plus minus. Whatever it is that these are going to be opposite signs. See the way they're an opposite way around here at this point? They're going to be the opposite way around when they...
So is there a point to that?
Yeah.
besides, because like plus minus 2 is just going to be, everything cancels out, no?
Plus, like
if it's plus or minus something,
yeah.
but if there's two of the same thing, plus or minus, doesn't have to be minus plus. What's the point of minus plus?
It's to distinguish the fact that if you have like plus minus x minus plus x, that no matter what happens, these are going to be the opposite sign, rather than they can be both plus. They can't. They'll either be, one will be plus, one will be minus, or if it's minus, this one will be plus. So you take, it's like that. It's that kind of relationship with them.
All right.
It's just based. All it's saying is logically, it looks a bit weird. Logically, is if one's positive, the other's negative, based off the normal slope thing. One's positive, the other's negative, and if that's the case, they'll always cancel out, no matter what the sign, the number is that they're representing, which basically leads to this. I got here eventually. There is no term after this. There is no term. There is no, because they cancelled out. This is the equation of the normal, and the equation of the normal has no plus c, if you wish. Now, I haven't seen yours, Rigel, but I presume you went down a similar line.
Yeah, I did the same exact thing. I just, instead of using a, I just said y1 as the variable, so I had two different variables. Instead of your plus or minus square root 1 minus a squared over a, I just had y1 over x1.
Okay, yeah, so you did the same thing. Yeah. The key thing here is there is no c, and if there is no c, that means this is a general equation for a normal. I haven't used any specific points yet. It's a general equation. If the general equation doesn't have a constant, therefore all the normals wouldn't have a constant, because no matter what the value for a here, there would be no constant c, and that's what we are trying to prove. Perhaps we got a little bit confusing with the minus plus plus minus. The whole thing is this term is the same as this term, and they will cancel each other out here at the end. Okay, so that's the way I proved it. Yeah, that was an interesting question. Question 14 then was the weird looking graph. It was like something like that. Oops, something like that. But the derivative, I presume, is pretty straightforward, using chain or product rule or something. Dustin, or not, Dustin's not there, but are you there? Can you have the derivative of question 14?
The derivative is 2x minus y all over 3y squared plus x minus 2.
Yep, spot on. And can I have the equation of the tangent that they illustrated? So they give you a 0.1 minus 1 somewhere here.
Yeah, exactly. So I just plugged it in for dy and dx, and
yep.
I got y equals 3 over 2x minus 5 over 2.
Yeah, so you plugged it into your derivative,
yeah.
And you got 3 over 2 is the slope, is it?
Yeah.
And then you use that point again.
x1 and y1, and then, yeah.
Okay, yeah. Okay, so it'll go in here, and you still have this point, which you can plug in as well, and you have your derivative. I'll just write the derivative here for Dustin if he watches the video. 2x minus y all over 3y squared plus x minus 2. All right, so that's question 14. Question 30 was an interesting one. It had for the function fx, it says that f dash x is greater than 0. It says that f double dash x is less than 0. Oh. Well, that's interesting. Let's see if there's any message from... anyone hear anything from Dustin? Is he all right? Don't have an email from him. Anyway, he might be missing electricity. All right. So what can we say about the function based off? Can you give me a general what you could state about the function, given that the derivative is greater than 0, and that the second derivative is less than 0?
The whole entire thing will be going up because the gradient's always positive.
It's always increasing. Yeah, it's always increasing. I mean, definitely say
And
that.
also, since the double derivative is a negative, it'll say that there are no negative turning points.
No negative turning points.
I mean, like it'll have stationary points, but it won't ever be like negative.
Okay, yeah. Can you speak to the concavity? Will it be
concave
It
down?
would be, huh?
Yeah, it's going to be concave down.
Yeah.
Now, does that make sense that something can be increasing the whole time and be concave down?
The slope just decreases.
Yes, the value of the slope. So if this thing is increasing, so the slope is getting bigger and bigger, but not the slope is getting bigger and bigger. The slope is decreasing, so it's just greater than 0, but it's starting to concave that way. It's concaving down. I think it's going to look something like that. Perhaps you got that. Okay, so let's have a little look at the questions anyway. Part A asks for find the equation of the tangent fx when x equals 2. So they give you some information for that. They say f of 2 is 1 and f dash of 2 is 2. So
They give you a point. 1, 2.
Yeah, they basically give you y1, x1, and the gradient. So
yeah, they're giving you everything here, aren't you? So you can go straight away. Y is equal to, what's the gradient then? So when we sub in to, the gradient is 2, isn't it? Sorry, are you doing y minus y1?
Yeah.
Y minus, what's y1?
y1 is 1.
Yeah, and then the slope we got here is 2. We know y1 is 1 because 1 here and 2 here. Yeah. And x minus 2 is net. And then you rearrange that, and I presume you get that 2x minus 3, I think. Okay, so hopefully you got that. Part B asks you to draw it based on. Okay, so you can sketch this and base it off that. So you probably got something like that, that curve, and then you've that line, something like that, going through. That's going to be minus 3 on the x-axis, on the y-axis up there. Where is it going to cross the x-axis at about? It's going to cross it when x is 3 over 2. Is it 3 over 2? So let's put it there. Or is it 2? No.
Well, they give you a point, and that initial f of 2 equals 1, so it crosses through the point 2.1.
Oh, yeah, they meet at the point 2.1, so my thing is off, isn't it?
Yeah.
If it's a tangent up here. Sorry, I was just looking at where this line crossed the x-axis. So it's up here. That's not, my sketch is terrible, but if I was in the exam, I might do that sketch again. But hopefully you can see it's this one. Yeah, something like that. So this is the point 2.1 where the tangent actually hits, and you can see that the curve something like that. So something like that. This line goes through minus 3 here, and this point is 3 over 2, I think, where the line crosses the x-axis. Okay, so that's my sketch. It's pretty terrible, but anyway. Explain why fx has exactly 1, 0. So perhaps Rigel, you can explain why this function only has one crossing point at the x-axis.
Because since there's no negative slope, then there's no way for the line to come back down.
Yeah. The slope never gets negative, and we need this thing to turn back down to hit the x-axis again. So some explanation of the f-x always increasing. And the last one, from estimate the interval in which the 0 of fx lies. Okay, so where does it estimate where it does lie? We don't have any information. Well, I suppose, if we look at the graph, it has to lie between there and there. Is that what we said? Between 3 over 2 and 2.
You just equate it to 0, but sir, I'm not exactly sure what it means by between those 2 points. Like, does it only have one point that it crosses through?
Yeah, it can only cross at one place.
Exactly. So I don't get this question. I mean, I got the right answer, but like I don't understand how it applies.
Well, you don't have enough. It never at any stage gives you the function. Like we are just dealing with a sketch of the function
Oh.
based off the information we got, based off being able to find the tangent and at a certain point, and the fact that it's always increasing. So our information is limited to that. So I would base then on the fact that I know that the tangent goes through 3, 2. Which means the function has to stay to the right of the tangent. It can never cross it. But it does touch at 2, 1. So it has to be between these two, where 3, 2 and 2, 1 on the x-axis. That's the way I read it.
No, yeah.
So it's between 1.5 and 2. So you can write that x between 1.5 and 2.
Yeah.
It's the only logical place that it could cross. Because it couldn't be... Yeah,
it's only because we're not given the actual function.
Yeah, it's because we don't have enough information. If we just had the function, you could easily get it, couldn't you? You can let y equals 0 and solve.
Yeah.
But we don't have enough information. That was the point. Okay?
I get it.
All right. Question something.
34 is what the Hospital's rule.
34. I haven't written this. 34. Oh, La Hospital. Yeah. All right. So La Hospital's thing, rule. What did these were like almost trick La Hospital questions. What was the what did you get for the first one, Badai? What did you get for the limit of the first one?
I got cos x over 6, which happens to be 1 over 6.
You got cosine x over 6? Okay.
Yeah, which is 1 over 6.
Yeah, that makes sense. Yeah, Rigel, you get the same?
Yep.
Okay, yeah. So you'll keep. I think you have to do it maybe twice, 3 times.
Yeah, you have to do it 3 times.
Yeah. Okay, it's 0 over 0 for a while, and then eventually you do get because 6. So x cubed goes to 3x squared goes to 6x goes to 6. Okay. Yeah. Right, and the second one, Rigel?
There's no limit since it's ex over ex. Their derivatives are always the same, so no matter what.
You eventually end up with ex over ex, or e to the 2x over e to the x, which means you can derive that forever, but you're going to get just infinity over infinity, aren't you? What did Badai? Did you get the same, Badai? What was your thoughts on that one?
Yeah, no, it does not exist because we have it's being 1 divided by 0, which is undefined.
You got 1 divided by 0, perhaps it is. Did you get 1 divided by 0, Rigel, or did you get...
No, I stopped because I saw e to the x over e to the x.
Okay, yeah.
Because no matter what it will be, it'll be infinity over infinity.
No, right. The second limit will be 2e2x plus 2x.
Okay, well...
that's what I got as well, over e to the x plus 4, and then next one, before e2x plus 2. But then that's just going to get a higher ex 2x.
Okay, well, let's Badai, how did you get 1 over 0? So your first derivative of the top... Yeah, it's going to be...
Because e to the power of...
Go on. It's going to be, 2e to the 2x plus 2x. Is it all over e to the x?
Yeah. Basically, it's just...
And you do it again. You get 4e to the 2x. I just want to get to the same page.
I just stopped right there, sir.
You stopped here? Or
right there, because the next point, the 2 will go to 0, and then it's just going to be 8.
Oh, yeah, there'll be 2 divided by 0.
On and on and on and on.
So it's going to be 8e to the 2x all over e to the x.
Yeah, and then that 8 will just keep on getting up by a multiple of 2.
Yeah, but what was you thinking? How'd you get 1 over 0?
I got 2 over 0 because e to the power of infinity is 0. So I got 0 plus 2 divided by 0.
Yeah, well, let's look at this stage. Infinity plus 2 is still going to be infinity, isn't it?
I thought e to the power of infinity is 0. Because
Number.
Yeah.
but
Is
if
e to
it's-
check e to the, well, you can do a very quick check. Do we have a calculator?
Well, e is 2.7, so 2.7 to infinity is not.
Let's just do it to a really large number. Overflow. Okay. It tends towards, not 0, it'll tend towards infinity.
Really?
Check it. Maybe I'm wrong. E is just, is 2 point whatever, 7-ish.
I thought, I don't know, maybe I originally thought.
Well, e to the 10 is look at that. That's a value.
Yeah.
E to the 10. So e to the 11, presuming e to the 11 then is bigger than that, which it is. It's multiplying by e. So e to infinity is just going to be a very large number. It's going to be infinitely large.
Yeah.
So infinitely large plus 2 multiplied by 4, whatever you want to do with it, it's still going to be infinitely large.
Yeah.
So I see this as what Rye just said, as continuing as infinity over infinity forever.
Yeah.
This is going to eventually end up this number will increase, but it doesn't matter because infinity is way ahead of matching that. So that's what I would say. Perhaps did you do that one with your tutor? Did they come up with something different?
I did a couple of questions with my tutor, but I attempted this one myself. I don't know. Maybe I originally thought e to the power of infinity was 0 or something.
Okay, perhaps you just.
Okay, but I understand why.
Okay, sweet.
Yeah.
Okay, well let's move
on.
on.
It'll be in this one.
Okay. Right, let's move on to the optimization questions, which was question 6, which was the open steel box question. If I can. So we got some steel box. You wanted the first part of it, so it was like so there's our sketch. This is X, and that's Y. And it's open on top. And the first thing it asks us to do is, so the capacity is 1 KL. So that's 1 KL is 1 meter cubed. I don't know if you knew that, but that's it is. So it asks for the volume of the box. So the volume of the box is going to be they're like x times y. So that's x squared y. So you would have got 1 is equal to x squared y, isn't it? And then it wanted y in terms of x. So a rearranging of this, divide both sides by x squared, and you get 1 over x squared is equal to y. Okay, did you both get that?
Yeah. That's for surface area, right, sir?
No, that's volume.
Oh, wait, sorry. Yeah, no, that's fine.
Yeah. Now, the total cost of the steel, now that's going to be dealing with surface area because we need so it's going to be the area of the base, which is going to be x times x. So that's part A done. Didn't ask for anything. We'll use this in part B because we now have a y in terms of x and x in terms of y. So the area, the steel is going to be the area of the base plus the 4 sides. So it's the area of the base is x times x, which is going to be x squared, plus 4 times xy, isn't it? Now.
And then you have to times by 2 for the cost.
22. Yes, because it's 2. Yes, multiply that by 2 because it's 2 pounds per meter squared. So this is going to give me in meter squares. Multiply that 2, and I'm going to also use y as what I found in part 1 over x squared. So that's going to be 2 times x squared plus 4 times x times 1 over x squared, like that. And then if I tidy that up, it was a show that, wasn't it? Show that, yeah. So once I tidy that up, I do get what I want. So that's 2x squared from that. And then that's going to be 8x over x squared, which is just 8 over x, isn't it? When the x is cancelled.
X squared is just it's just the base, right? Because it's x times x.
Yep.
Yeah, and then okay, xy would be the
yeah, the side. So if we look at the diagram, x times
there's
only one of us. There's 4 of these, 4 sides.
Yeah. No, but there's only
one base.
yeah, exactly one base. Yeah.
One base, 4 sides. Yeah. So that's why there's 4 xy's and only 1 x squareds. But we're multiplying by 2 because the cost was 2. Okay. Part C, I'll do it on the same page. Part C asked us for something. Find the dimensions which would cost the least to make. What's the dimensions? Okay, what's the dimensions you got, Rigel?
That x is the cubed root of 2, and y would be around 0.630.
Okay, so in order to optimize this, we're going to need to. Well, what do we need to do? Badai, what do we need to do in order to optimize to find a max or min?
You need to find the turning points.
Yeah, so I need to find the turning points and let it equal to 0 to find either a max or a min, yeah?
Yeah, but we already did the. Well, I already did the derivative previously, so we just plug in like.
You've already done the derivative? Oh, that's good for you. I haven't yet. So let's get the derivative of this thing down here. So the derivative would be, well, that's 2. That's 2x squared plus 8, the x to minus 1, isn't it? When I derive that, I'm going to get 4x minus 8.
8x over.
Yeah, or over squared.
Yeah.
Yeah, that's probably nicer to have it over squared. Okay, so
then
that's
put it to 0. Yeah.
Solve this then, I suppose. I think you're going to get, yes, okay, you're going to get exactly what Rigel got. That comes over comes plus, that's 4x, 8 over x squared. Multiply both sides by x squared, you get 4x cubed is equal to 8. And then I just want x cubed on its own, so that's 8 over 4, which is 2. And then I need the cube root of 2, then would be my x. Okay. You can test if that's a minimum or draw a sign diagram or something.
But I also got x equals wait.
Mm-hmm.
Never mind. Just cube root of 2. Yeah.
Okay, and then to find the corresponding y value, you can sub that in to your original equation, 1 over x squared, and you get whatever y is. And I trust that 0.6, whatever Rigel said, was that applied.
We get three values, right?
No.
No, you wouldn't get 3 values. It's just the cube root of 2. Cube root of 2 is the decimal answer in itself. I've forgotten math. The cube root of 2 is 1 point something.
Yeah, and then you get 1 over cube root of 2 squared.
Yeah. Yeah, so it's just there only is one answer. So it's 1.26 is that
Yeah.
in meters, and 0.6 when you square it. It's going to be 0.63 squared, yeah. No.
Wait, what,
sorry, 1 over squared. 0.6. No, I just squared it. It's 1 over squared, so it's 0.63 rounded is the y. The height. That's the height.
Yeah.
And just
Okay.
when I put this back into this. Yeah? Did you get 2 answers, Badai? No? We've lost it. All right. I take it as that's okay. I can move on. Question 7. All right. So question 7 says, on the Indonesian coast, this is the main reason I picked it because it said Indonesia, the depth of the water T hours after midnight was given by this thing. 9.3 plus 6.8 cosine 0.507 T's in there. What does the derivative tell us? What is the derivative of what? So the derivative is going to be dt, dd, dt. The rate of change of the depth of water is it and time. So when you do get the derivative, 9.3 is going to disappear. it's going to be 6.8 times, well, minus sine is the derivative of that, and you're going to still have that inside the brackets. And then you need, so a chain building it up. And then the derivative of the function inside is going to be 0.507. We okay with that?
Yep.
Okay. So that's the derivative. You could tidy it up. You can multiply that by that if you want. It's not necessary. And you can multiply it by -1. You can have the minus outside all this if you wanted. Perhaps it'd be nicer. Yeah, so what does that tell us? Right, so what does it tell us?
That tells you the rate at which the water is changing at any given time.
Yeah, so any time after, if you know the number of hours after midnight it is, you can tell the depth of the water based off a function, which is kind of cool. All right, so that's part A. Part B, so if you had a time, you could just sub in for T and you have the depth of the water. And that's what you're doing in the next part. What is the depth of the water at 8 a.m.? So that's 8 hours after midnight. So that's put in 8 here. And I have an answer of 5.15.
Yep.
Yeah. Okay, so if you put in T.
The initial equation, not the dy dx. Because it's just asking for the depth, right?
Oh, yeah, they're not. Yeah. No, exactly. Very good. So the depth is going to be about 5.15. So you can put it in here. That's just getting, this will be the rate it's changing. And of course, this is the actual depth. Good spot. Yeah, it's not that. Thank you. Part C then asks if the tide is rising or falling at 8 a.m. And that's where we put it in here and we get an answer for T. Yeah. Now, I think if we put it in, you get, or you get an answer for dt, the change of the depth of water.
Yep.
What did you guys get for that? Anyone have an answer?
2.731.
Okay, so it's 2.73, 3 significant figures, so you'd stop at 2.73, which of course is a positive number. So what does that tell us?
It's increasing.
Oh, yes, but okay, so it's rising. Yeah, it's increasing or rising at this rate. Yeah.
I'm just wondering, like, I always do it to 3 significant figures, but do you lose marks for not putting 3 significant figures?
Yes.
Like if it specifies, yeah, but if it doesn't really specify,
you could lose a mark. Yes, you could. Okay. Depends on the mark scheme that particular year, and depends on the type of question. I think if you said what Ryan just said there, 2.731, you wouldn't lose a mark. But in general, get used to IB maths. Just do 3 significant figures, unless it says otherwise. I would do that, and then state that you've rounded to 3 significant figures, just in case they you weren't supposed to. I just do that by a rule. But it does say it in the mark scheme, but I think it's one of those things where if you appealed, you get the mark back. So therefore, they generally don't mark you down for it. So don't worry too much about it. Just try to remember it. All right. So the last part: at what time or times is the tide highest on the day? In other words, and then find the maximum depth of the water. So, right. So we'd have to let this equal to 0 to find a maximum. Would we? Did we get an answer for this?
Yep.
Okay. Rigel, you seem to have an answer. What's your answer?
Well, again, you wouldn't plug it into that, or you would, and then you would get time is 0, so then the depth would be 16.1 meters.
Yeah. Okay. So in D, part D, you know that you have to let this equal to 0, so to give a max or min. So if you let that equal to 0, then let this equal to 0. The only thing T could be is itself 0. How did you get 16.1 then?
Plug it back into the original equation.
Oh, okay. So you plugged it back in here, and therefore you would get,
cosine would just be 1 or whatever.
Yeah.
If that's 0, that would be 1, then it's just 9.3 plus 6.8.
Yeah. Exactly. So you'd end up with at t is 0 then, d is equal to 9.3 plus 6.8 times cosine 0, which is 1. So it's just times 1. And add those together and you get 16.1 meters.
Sir,
Yes.
do I have to remember the trigonometric radiant table values? Like memorize them?
Yeah. Yeah, you need
Okay.
to always know them, yeah.
Alright.
All right. And the last question, which I will preface by doing related rates in general, and then I'll actually do the last question. Right. Okay. So related rates is you may, if you looked it up on the internet, you may have seen a ladder example used. Perhaps you did, perhaps you didn't. There's also one in the book. The slipping ladder is used a lot. So the question is, you have a ladder up against the wall. So let's say a wall here like that. And you have a ladder of 10 meters lying up against the wall. So that's a 10 meter long ladder lying against the wall. And the question is, how fast, so if it starts slipping, how fast is the top of the ladder slipping when the bottom of the ladder is a certain amount from the wall? So let's say the bottom of the ladder moves at 1 meter per second. It slips that way at 1 meter per second. And at this particular point, we're going to say that it is at 6 meters from the wall. Okay, so it's 6 meters, and it's slipping at 1 meter per second. And we need to find out what's the rate at which the top of the ladder is slipping. In other words, what's the speed at which the top of the ladder is slipping. So that's okay. That's the question. So in these kind of questions, we need to think about what's constant, what changes, and what equation links everything together. So perhaps you recognize that as a right angle triangle, which of course it is, which means that an equation that would relate these two together is Pythagoras. X squared plus y squared equals 10. So no matter how much the ladder is slipped down, so let's say it's
equals 10 squared.
No, 10 squared, thank you. No matter if it slips down, it's still x squared plus y squared is going to equal 10 because the ladder length is constant. It's not. You can't change the length of the ladder. Now the lengths of x and y will change, and the speed actually, which it's slipping, is a constant as well of 1 meters per second. All right. So we need to look at how this equation changes with regards to time. So we need to derive it with respect to t. So let's do that. So let's do d dt of x squared plus y squared equals 10 squared. I suppose you can put them all on one side if you want. Okay, so this is a bit weird. What's the derivative of x squared with regards to t?
2x.
It's actually 2x dx dt. So it's a bit like it's
The chain rule?
It is the chain rule. Yes, exactly. It is the chain rule. Yeah.
Oh.
So it's a function within a function. Again, it's the same as what we did with the implicit differentiation before. And the related change of y is the same thing, 2y, but dy dt. Because the chain rule, again, it's a function within a function. And then 10 squared is still, the derivative of a constant is still just going to be 0. So we had this new equation. Now,
But sir,
yes.
Wouldn't d over dt also multiply with y squared?
Yeah, it does. Yeah, you're doing all the bits separately. So what's the derivative of x squared with regards to time? It's 2x, and then the derivative of x with regards to t. what's the derivative of y squared with regards to time? Is 2y, and then the derivative of y with regards to t. So it is doing both using the chain rule.
But what about
the 10?
Oh, no. Okay. No,
10 is just a
sorry.
constant,
Yeah,
the same as anything, because 10 is going to go to 0. You could say 0, d10, dt.
So, sir, you would only do 2x if it's dy over dx, not dx, not d over dt, right?
You would only do.
No, like it's only 2x times dx over dt because x is always changing, or something.
Yeah, so we're deriving with regards to t. It's not deriving x with regards to y is what you normally do. So you're deriving just x. This is x with regards to t.
No, but there are some other questions.
Yeah, there can be asked a number of different ways.
Some other questions that had like dr over. Okay.
Yeah. So like in the last question, it was d over dt, or dr over dx, or it's whatever's changing in relation to the other thing. So we're trying to see how these change with regards to time. So it's a function within a function there. Let's watch the way you finish the question. Maybe it'll make a little bit more sense. So what are we trying to find? Which one of these is the one that we don't know? Is it x, y, dx dt, or dy dt? Which is the one we're trying to find? So the question was, at what rate the top of the ladder is slipping down the wall?
We're finding dy dt then.
We are finding dy dt, because this would be y, and the rate at which it slips is dy dt, which means that's the only one we can leave blank. We must be able to fill in the other ones. X, well, that was given. That was 6 meters from the wall. So x is 6 meters. 6. Y then, we don't know y. What's y going to be?
We write it.
Wait, so how did you get x equal to 6?
I was given in the question. It was given. Sorry, I didn't write out the question full, but 6 at 6. It was like at 6 meters, and it's traveling 1 meters per second. What's the rate at which it's slipping down? So y can be got, of course, because if we know that x is 6, we can just use Pythagoras Theorem to find out what y is at that exact moment that x is 6, because they have to square to reach 10. So you can do a quick Pythagoras Theorem. 10 squared is equal to y squared plus 6 squared. 10 squared minus 6 squared is equal to y squared. That's going to be 64 is equal to y squared. So y is going to be 8. It can't be minus 8, of course, because it's a sign. Okay, this diagram is way off, but hopefully you can see that it would equal 8. And dx dt then is another constant. It's constantly moving at 1 meters per second, which was given in the question as well. All right. So we'll do the question you have to do, where you'll see the question written, and perhaps it'll be better. But the idea here means that we have now 3 out of 4, which means we can find the fourth. So x is 6, so that's 2 times 6. Dx dt is 1. 2y then is 2 times 8, and dy dt is the unknown. So that's what we're trying to find, the rate at which it's slipping. Now, I kind of hope this to be a negative number, because it's slipping down. And it is going to, that's how we're going to get a negative number, because when that subtracts over to this side, I'm going to get, and that comes over minus 12, isn't it? So dy dt is then minus 12 over 16, which is minus 3 over 4. And that kind of makes sense. That's minus 3. What's the units we're using? It was meters, and it was second. So it's slipping down at negative 3/4 of a meter per second. Whereas the x was slipping over at 1 meter per second. So there are different rates of speed.
Sir?
Yes.
I'm a little confused how it's 2 times 6 times 1 instead of like 2 times 6 times 6 over dt or something.
Well, dx dt is the rate of change of x with regards to time.
Oh, I mean, yeah. How did you find dx dt equals 1? Oh, okay, yeah.
We are told at the start of the question that the speed of the ladder slipping this way is at 1, the rate of change is at 1 meter per second. So meters, that's the x distance, and seconds is time. So that's the change in x with regards to time.
Okay.
That's what, whenever you see a speed, is the change in kilometers with relation to hours. 60 kilometers an hour. It's a rate of change. So
Okay,
now, yeah, I think just the more examples of this you do, the more you get the hang of what's changing and at what rate, and how do we, well, I suppose, label the letters. But hopefully it makes sense that it would be slipping down the wall at 3/4 meter per second, and that one's moving to the right at 1 meter per second. Okay, so I need to find that last question you guys had. It was a dude in a boat or pulling a boat or something like that. Where is it?
Yeah, it's a bit backwards since you're trying to find.
Okay, so we're going to be using Pythagoras again, aren't we? Yeah. Okay. So let's get this. Okay, so I don't know if you can see that, but let's. We're going to redraw it because with these related rate questions and optimization questions, if they haven't drawn a diagram, definitely do, or if they have, definitely improve upon it if they haven't. So something like that. Okay, there's our right angle. So am I right in saying this is L then, I think, from the question? Or maybe it was just I used the label L. Okay, so that's L meters, whatever, the length of the rope meters. Don't know what it is. Very similar to the one we had before. I think this is 5 then, isn't it? Because it's 6 take away 1.
Yeah, that's what I did as well.
Yep.
Yeah. 5. And then that this length, let's call it x. So the relationship between these and Pythagoras is x squared plus the 5 squared is equal
So
to...
doesn't it say
L squared.
at the instant one it is 15 meters from the jetty?
No, I haven't. Yeah, I haven't put stuff in yet.
Not yet.
Oh, okay.
Found a general equation first, and then I'm going to look at the rate of change of this with regards to time as well, similar to the last time, because things are changing with regards to time. He's pulling the thing in, isn't he? So let's look at that. So how this changes over time is going to be the same as last time. So with regards to t, d dt of all this is going to be same thing, 2x dx dt is equal to, well, this cancels, isn't it? So we don't, or not, disappears because it's constant. This one's going to be 2l dl dt. Okay, for the same reason as the previous example. Okay, now we have the rate of change in general with regards to t. Now we look at this particular case. Okay, we look at what information we're given and can we replace this? Right. So you're saying you're right. So how fast is the boat approaching the jetty at the instant when it is 15 meters from the jetty? So that means that x distance is 15. So that's something we can say. X is 15. We haven't used the 20. So he's hauling on this rope. He's up here. He's up here and he's hauling in this rope. So this rope is shortening, isn't it? It's getting shorter if he hauls in this rope. The length of that rope is getting shorter at the rate of 20 meters per minute. So the length of the rope is shortening with regards to time. What could I say it is? 20? Is that okay?
Yep.
Yeah. I put it as minus 20 because it's shortening. I don't think it really matters, but I put it at minus
Okay.
20 or minus
Wait, but
20.
sir, theoretically, that means he'll pull the boat in under a second towards him, right?
This is per minute.
Oh, sorry.
Meters per minute, isn't it? Yeah, so he will. I reckon it'll take around a minute because, of course, this L distance is going to be the longest. I know this is 15, so that's good thinking. 15. This is still going to be 5, and we're going to use that in a second. Okay. So we have not enough information to solve this yet. We have 2x, because we know 2 times 15 is 30. And we have dl dt. What are we looking to find? Are we looking to find L or dx dt?
dl dt.
L.
Wait.
No, the rope is attached. How fast is the boat approaching the jetty at the instant when it's 15 meters?
dt. I don't know. dx, I guess.
Yeah, it's going. If this is getting the boat,
dx
it's getting
dl.
closer and closer.
dx dt.
dx dt. The rated change of this x regards to time. Yes. We have the instantaneous point, so it's 15 meters. At that point, what is its change? How fast is it going towards? So we're looking to find dx dt, which means if I look at my thing, I have that. I need to find that. That's okay. I have this, which means I need to find L. How do I find L?
Pythagoras Theorem.
Exactly. Yeah, so I know that L, it's 5 meters. That's constant. That's 5. I know that X is 15 at that point. So if I found out what L is at that point, I would have the value for L at that particular moment. Sorry, I drew it off screen, but here. So let's get that. 15 squared plus 5 squared.
Like 15.811.
You got it? Let's make sure you're right. Yeah. So that's 15.811. Okay. Don't need to do three significant figures yet because it's not my final answer, so I'll keep it as a larger figure. So now I have L at that exact moment, which means I can solve this equation. So 2 times 15, 2 times x, dx dt, I don't know, equals 2L, as we got this decimal here, times dl dt, which was negative 20 or 20. You're going to get, it's not going to affect the answer. You're either going to get a plus or minus, you just have to refer. So let's just take it as we use it as plus 20. Okay, so that now divided by that is going to give us the x dt, isn't it? Which is around, did anyone get that? I think it's around 21. I did this earlier. 21.1 meters per minute. Sorry, unit was not meters per minute. Okay. So the boat is approaching the dock. There's our boat. It's approaching the dock at 21.1 meters per minute, which makes sense because he's pulling this in at 20 meters per minute. So it's going to definitely take less than a minute to cover the rest of the distance anyway. And that's all we need. That was the answer. 21.1.
Wait, sir.
Yeah.
Oh, okay. Yeah. You did 2 times that because it's 2x. Yeah. Okay.
Yeah. It was 2L and 2x. Sorry. 2L and 2x. Okay. So I'd recommend doing more of those related rates questions. The key thing is don't substitute in too early. Derive it first. Get a general equation using variables that you're looking at. I used 5 here because 5 is never going to change. The dude's height was never going to change. The distance here is never going to change. So you can use that in the original. It's a constant. Whereas x and L were variables. X was getting shorter and L was getting shorter. They're both getting shorter. And you had to look at the rates at which they were getting shorter. So hopefully that made some sense for related rates. Okay. Let's cut that video. All right.